So in this video, we're going to be talking about limits again, but this time in a more formal way. In the past, we've talked about limits as kind of that value that our y coordinates converge on as our x coordinates get closer and closer to the value to another certain value. But that it's kind of, I want to say floppy, that definition. It's squishy. You can't really mathematically use it. It's really just an intuitive way of thinking of limits. What I'm going to teach about in this video is called the Epsilon-Delta definition of limits. And epsilon and delta are these two characters here. This one's epsilon. They're in Greek characters, epsilon and delta. And these are going to represent little intervals, but we'll get to that. So on our function, we have some value c. I'm going to mark that here. Some value c. And for that c, we know that there exists some value. It's kind of unclear what it is yet, but there's going to be some value here, some limit, and that's going to be our L. Some limit called L. Now, we can't really say what this limit is, right? I mean, x, this function, f of x, might not be continuous, and we can't just plug c in, because for a discontinuous function, remember that we cannot merely say that the limit, I'm going to use cursive here, as x goes to c, our x values goes to c, of f of x is not necessarily equal to f of c. For a continuous function, it would be, but, it's kind of, I'm going to put a little, I'm making notation up now, but it's not necessarily equal to f of c. So how can we define this limit otherwise? Besides using our floppy, oh, it's getting close to this. No. So what we're going to do is say, okay, so we choose some interval. We're going to choose some interval delta around c. This is our interval around c. Right? So here's c minus delta, and here's c plus delta. And if we choose x values within this interval, if we choose some value x here, if we choose it inside this interval, then f of x, our point f of x, will be also inside an interval, but that interval is going to be called epsilon instead. We're going to have L plus epsilon up here, and, well, yeah, so it's going to be like up here. And we're going to have L minus epsilon up here. So if we choose some closeness, delta kind of represents a closeness that we can get to that point that we want to find the limit of. If we get some closeness delta, there's another closeness that corresponds to it, epsilon, on the y-axis. So if we get this closeness to c, we'll get some other closeness to L. So how can we express this idea? So we have that, right? This is our x value. So if we find the distance between these two, that's going to be x minus c, and x can be down here too. So if we want to make this positive to represent distance, like the length of an interval, not as distance in the idea of physics, but distance in the idea of math, where it's just the difference between two spots positive, we take the absolute value, and that has to be, first of all, greater than 0, right? Because this x minus x cannot be equal to c, right? Because when we're trying to find the limit at x equals to c, and we can't just plug in c and find, f of c, because that's not going to be the limit. So, and if that's a confusing idea, we can answer any questions in the comments, but for it to be an interval, it has to be greater than 0. It has to have some length. But it also has to be less than, right? We said it was between delta. So the distance between these two is between delta. And similarly, if we take the difference between f of x And our limit that we're trying to find, right? That's this thing here, L. If we take the difference between those and the y-axis, and we take the absolute value of that, I don't know why I put brackets here instead of the proper absolute value symbol, that 2 has to be greater than 0, right? An interval has to be greater than 0. And it has to be between our epsilon distance, right? So the distance here is more like this. That's our interval here. This is f of x minus L. And it's going to be smaller than the total epsilon. Now, how does this define limits? Because this is what the Epsilon-Delta definition is. This is our Epsilon-Delta definition. What does this say, though? What this says is essentially a way that we can basically solve for L and show that L has one value that is defined, our limit. We can specify the limit mathematically. Because, as we said earlier, our epsilon value here will be some function of our delta. The epsilon will be some function of delta. So the epsilon will be some function of delta that's usually actually the function of x, right? Because we're essentially trying to find a y-coordinate that makes an interval that corresponds to the x coordinates interval. So we're going to use the function f of x. This may not always quite be the case, but this is usually what you'll see, that the epsilon will be the function of the delta. But it might be it's going to be some function. We can call that function h of delta. But usually these will be the same thing. And so what do we know then? Basically, we choose some delta. We can get as close as we want to that c. We choose this. So we choose this, and now we can solve for our x because we know what we're trying to get to. We know this. So we can find x, as long as it's not c, right? So we can find this. Now, if we go to epsilon, using this function that we know, we can find what epsilon is. So we can find this with what we know the function is. So we can, if we know how close we want to get in the x-axis, we can find how close we're going to get to our limit in the y-axis. So we solve for this, and now we don't know what limit is, but we do know what f of x is because we know what x is. As long as x is not equal to c, we can define f of x. That's the point. So f of x, we know what this is, right? We just plug x, so we use what we know x is that we found to find our f of x. And you'll notice we know this, we know this. What we can do is, because we can make delta and epsilon as small as we want, we can solve for what L is. Does that make sense? Because now you might say, oh look, but we have an inequality. So we're not really solving for any of these. But if we can make delta go almost down to 0, like as close as we can to 0, and make epsilon go as close as we can down to 0, there's only one value that will make this true all the time. Because there has to be a value that's between this value that's almost 0 and between actual 0. And there's only going to be this, as we get smaller and smaller and smaller, there's only one value that we can sort of solve for. Not really solve for algebraically exactly, because we can't really do that in an easy way, just with plugging it in, because as you may have noticed, we're dealing with inequalities, and we're not really finding, it's kind of not really finding x. We're finding that there's this one value for which this will all be true. And that's going to be that L that we're trying to find, right? So we have this, because we can make delta almost down to 0. And because we can choose any delta we want, there will only be one L that makes this between these two zeros. This is a rigorous definition, and it's kind of unintuitive when you first look at it. So I'm going to, well, let's write this out again. Let's write this out again so that you can see it. If you just need this for your class, oh dear. This is the Epsilon-Delta definition of limits, and it rigorously and not floppily, as I like to say, kind of proves the idea of limits and can identify that a limit exists. But if my explanation was not really intuitive, that's okay. You can ask about it in the comments. It's kind of weird when you first go into it, and we won't be using this a lot until later on. But I think it was good to discuss. Thanks for watching.